and a half, and then my second was like a 3.5.
Wow. That's awesome.
Mm.
Cool. John, do you have a good break?
Yep.
Yep. Here we go, gentlemen. Nick, you good to go? Let's see. Roth, Garrett, how you doing?
Doing
Now,
good.
Joseph, how come I have you on here in two forms? One for voice and one for video?
Talking to me, ma'am?
Joseph Khaleesi, yes.
Yeah.
Okay.
So you
one.
just talk to the white square. That's the one I talk through.
Oh.
This is the one you can see me through. That one is for talking to me.
Instead of talk to the hand, it's talk to the white square.
Indeed.
I like it. I like it. Okay.
can
Well, it's
change it.
nice to
Hold up.
see you. I know that was a challenge before break. I appreciate that you were able to get the video up and going. So it's nice to finally see your face and get you in there. So hope you're all doing well. We can do this, right, guys? May
Yeah.
21st. I mean, that's our last day. As much as I miss you, I think you guys are doing really, really well with the online. I'm actually very excited about what I've learned in doing all of this. And I think going forward, it's just going to help us next year, quite honestly. So one thing that's come to my mind, I think I'm going to utilize next year, because you guys all know I felt like our classes were just always so short. So there's a methodology out there called Flip Your Classroom, where you would watch the lecture for homework, and in class, you are working over the problems. Like we would do that kind of work, because that's where you need me. You need me when you are like doing your homework, not writing notes. So I love that idea. And I think next year that's what I'm going to kind of do, now that I know how to videotape myself. And your homework would be to watch the lecture and take notes. And then in class, we actually kind of do your homework. So you flip it. So I think I'm going to try that. So any of you guys that I have in the future in Physics 2 and stuff like that, which I look forward to all of you being in there, that's mine. I think I'm going to try out if our schedule stays the same. I also, though, really like the block scheduling where you go every other day. Doesn't that
We
help
only
you?
have you 9 more times.
I know. It's going to go so quick. So I have a lot that I want to go through. Joseph, I like the white. I like the white. Now I got to talk to SpongeBob.
Yes.
I rarely watched it, but when the kids were little, when you guys were little, maybe you went to King's Dominion and they had the SpongeBob like thing that you sat in and it moved around where you went under the sea. Oh, it made me nauseous. So Joseph, I'm not gonna lie, when I see SpongeBob, it makes me a little nauseous.
I remember that.
My
So
stomach
change
can't
it.
handle those kinds of rides. But it's okay. If that brings your smile, we'll keep them up there as long as I can see your happy face as well. All right, any questions or comments from you guys before we get started today? Matthew, nice to see you. Welcome. Okay, gentlemen, today, so I'm going to do a combination. We're going to do some concepts. I have some lab equipment here with me, so I'm going to be moving my computer back and forth along with the whiteboard. We're going to go over some concepts. So bear with me as I move that. I hope that you all put your screen in speaker mode. And then you can also, on the upper right corner, if you haven't been already doing, click the single bar and it eliminates everybody's faces. And I think it allows you to be really concentrating on what I'm doing. I do try to pin my video, but at the same time, how you can control your screen, I try in a lot of our meetings, and it helps me when I kind of eliminate everybody's faces. And you do that, if you go over up above everybody's faces, you'll have a single bar, a double bar, and then the grid. You do the single bar, it eliminates faces, and all you see is the name of the person talking. Okay? All right, well, let's begin. John, you want to give us our prayer this morning?
In the name of the Father, and of the Son, and the Holy Spirit. Glory be to the Father, and to the Son, and to the Holy Spirit, as it was in the beginning, is now, and ever shall be, world without end. Amen.
Excellent. Thank you. All right. And of course, how many more days, Tucker? 8? 9?
9.
9 more mustard seeds. Here we go. I know. I'll keep sending them to you over the summer. Let me get out my old lady glasses. April 21st. This one, I am a sinner. Reach this awareness. Make this confession. It is the first condition for salvation.
Just gets me going every day.
What's that?
Just gets me going every day.
Get to be the mustard seeds? Yesterday's.
This Liza Weaver.
Since now I only see you every other day, I'm going to read you yesterday's. This one was good too. You seem intent on taking the easy road, and I've tried over and over to gently persuade you not to. Let me tell you plainly and clearly, the easy road does not lead to heaven, and there are only two eternal destinations. And my comment yesterday was, the easy road does not lead to good grades on your transcript.
That's deep.
This
All
Liza
right,
Weaver.
gentlemen. First, I want to thank you all because you did fabulous. All your work is in. We are ready to go for the last stretch here. Everybody has nothing missing. So I really appreciate that because it's such a headache to go back and grade work that is missing. So we want to continue today. Anybody remember, Nick, what were we doing before break? What concepts were we going over?
I have no idea.
No idea?
I don't
Ryan,
remember.
Impulse.
impulse, which causes a change in?
Is it a change in momentum?
Change in momentum. So if I apply an impulse, which is a force over time, I cause a change in momentum, right? So let's review that. So you already have this in your notes, but is everybody ready and prepared? I'm going to give you some more notes today. So make
Hold
sure
on.
you take paper and pencil ready. Get that all ready, and we're going to begin review here a little bit.
This
All right.
Liza Weaver.
Yes, Ryan.
Next year, you should see if you can start saying the mustard seeds in the morning announcements.
Oh, do you like them that much?
Yes, we should. That should be something we
Yeah.
start our day off with.
I like it.
Bro,
I
if
can
you
ask.
started the volleyball team, you got to use it at every practice and before.
Oh, I
you
would
guys
do
like
that.
before a
Tucker, that's
game.
so funny you say that to me because there was a thought that went through my head this morning because I've been avoiding getting involved too much, and I'm thinking, do I really want to get volleyball? I love volleyball. I just don't know if I want to put
They
the
need to
time.
make it so it's not during football season though.
I know. It
I
would be
swear
tough.
there's like another season for it.
Maybe we just develop, maybe we just have a club team.
Oh
They-
yeah, do that. Like
could
in
have
the
a club
winter,
team that
because nobody
competes in
plays
the,
winter sports.
Yeah, so we
basketball.
could just play at the club at Richmond Volleyball Club and have a club team. They do
Yeah.
That would be
Okay.
sweet.
I would do that,
idea.
yeah.
I like that idea because
Because that would keep everybody in shape.
Yeah, because I didn't do something in the winter. I was gonna do
Yeah,
I
same. Like
I
I
can't
would
do
actually
like
would
our
allow you
games
to
up
play
late.
sports at Benedictine and that because they compete on the weekends. You would compete like on Saturday tournaments and stuff.
Well,
so-
football does
I
it
can't
on
do
weekends
that.
though. Football plays on weekends.
Hector, that was you. You can't do weekends.
No, because every other weekend it's like a wrestling team meet or
Oh,
something.
you're right. Wrestling. Well, we could maybe do it in the spring. I don't know. Anyway.
No, not
back to
spring. Do it in the
physics.
winter.
Everybody else has
Do it in
baseball.
the winter. The winter is
Winter.
the best.
Winter, yeah.
Well, we could do
Because there's
both.
gonna
I
be
mean, if you're in a
extra room
club,
in the new
play-
gym.
My club team plays 4 seasons, winter, spring, summer, and fall. So we play all 4. So it would just be that we mix up the team every season, whoever's available.
Oh wait, you said in summer?
Yeah, we play in
Oh.
the summer. Mhm.
Yeah, you
Well,
could do like
if you
June
were
and
to do that, you're in
July.
like a league. You're playing in a league level.
You could
which a lot
do
of teams
June
do.
or July.
I know St. Gertrude played in a women's league, on the off season. But all right, gentlemen, back to physics. So as Ryan said, let me put this up here. Just a quick review. And while I have it up, make sure you all write this down. Here's your homework for tonight. I want you to take a look at section 6.5 and 6.6 in your textbook. So I always write the sections because some of you have edition 11 and some of you have edition 12. So depending on what edition textbook you have, okay, the pages may not be the same. So for my book, edition 12, it is pages 97 to 101. That'll be the background information, what I'm going over right now. And then there's a worksheet. So
I
one
have
thing
11.
What's that? Yeah, if
I
you
have
have
the
11,
11.
I don't know what your pages are, but it should be the same section, 6.5 and 6.6. The worksheet that I put together, I typed up the questions at the end of the chapter, so we're not worried about which questions they are.
Do you know what
Everybody?
chapter it is?
I'm sorry, Tucker, what?
What chapter?
chapter 6, section 6.5 and 6.6. All right, so your homework, everything will be graded every day. So what I'm doing on Blackboard is I'm now attaching these sheets to assignments as opposed to putting them as documents. So I think that makes more sense in how most of your teachers are using it. So if you have trouble with any of that, please see me, but know that it is always to be submitted through Blackboard and due the day of your class by 9 o'clock in the morning. So it's not due when class starts or after, but it's due that morning up.
Is
Okay,
it start of chapter,
everybody got your homework for tonight?
start of chapter 6?
No, it's 6 point. We already did the beginning, which was momentum and impulse. So now we're in the middle of the chapter.
All right, I'm at chapter 6. I just can't find what the.
It's called collisions and conservation of momentum. You might not even need it because I'm going to give you the notes right now.
Oh, didn't.
So
I'm about to look at- I'm
it's
about to
just
look at
another
the-
reference. So if you're not following along with the notes, hopefully from the notes you can do your homework, but this is just another reference in your textbook. Okay, I'm going to mute you guys and start our notes here.
Oh, Miss Rosemary,
Raise your hand if you have a question. Ryan?
I'm about to go get. I need to go get a new pencil.
I'm sorry.
I need to go get a new pencil out of my room. 'Cause
That's
I-
fine. This will just be review. So I'll give you a few seconds here. All right, gentlemen, here we go. Day 1 of 9 days. We can do this. Okay. So for a quick review, as Ryan had said, what we did before break was talk about momentum, right? So momentum was equal to, we gave it a letter P. It's a vector quantity, and it is equal to the mass of an object times its velocity, right? So I'll put an arrow like that. So that was our equation. You guys do great with your math. So I think that makes sense to write things as mathematical equations. So momentum was a mass of an object times its velocity. Anything not moving does not have momentum. So what we saw is, well, if it's moving and it changes its velocity, that's really the definition of acceleration. So we took Newton's second law, F equals ma, right? So we had Newton's second law. And again, you already have all this. This is just to remind you what we were doing before break. F equals ma. What we did is we wrote A as change in velocity over change in time. And we ended up with the momentum impulse equation like that, okay? So that's what we were using before break. This side was called impulse. So impulse was equal to force times time. And that impulse, right, caused a change in momentum. I guess for that, I'm going to write that as an equals. So what we saw before break was it mattered how long my hand was in contact with something. So whether I was pushing something or catching something, it mattered that time. So up until then, when we were doing Newton's second law, we didn't worry about the time of the force. This considered the time, and we put that in, and it mattered. What that did was change the momentum of an object, okay? Now that force came from the outside of the object. So remember way at the beginning, it's an outside unbalanced force that changes the momentum of an object. Newton's first law, law of inertia. We need an outside unbalanced force. So we want to concentrate today on what's really meant on that outside, right? So any force coming, if I would imagine a boundary system around, a boundary drawn around my system, anything coming from the outside would be this force that would be applied over time, causing a change in momentum, okay? But if I enclose my system so that everything that's happening is inside those boundaries, then I have only internal forces. And internal forces do not cause a change in momentum. And that's what we're going to focus on today and Thursday. So in the absence of an outside unbalanced force, what we say is momentum is not changed. It is rather conserved. So today we're going to talk about the conservation of momentum. Oops.
Miss Risenweaver,
Yes, Hector.
if we forgot about all that impulse stuff, where can we read about it again in the book? Like what pages and stuff?
This is all chapter 6.
Okay.
It should be at the beginning of chapter 6.
Okay.
Best thing maybe to do, Hector, remember we did 2 worksheets on it, is maybe go back and review those worksheets.
And those are all in class documents, right?
They should be, yes.
All right.
Yes.
Thank you.
Now, the other thing I did for you guys, I had some other students show me what it looks like from your perspective, and it looks like all your class documents kind of show up. It gets really congested. So I did go in and remove past ones. I kept all the momentum ones. So Hector, I think it's still there. If not, just email me and I'll email it to you directly.
All right. Thank
So
you.
I tried to clean that up for you for the last couple of weeks so we can easily find information, okay?
All right.
All right, so the conservation of momentum is what we want to concentrate on today. So what we're going to do is we're going to eliminate these forces. There are no outside forces. What the conservation of momentum says is the momentum, or the total momentum of a system before an event, is what I want to write here, of a system before an event is equal to the total momentum after the event. Okay? The total momentum of a system before an event is equal to the total momentum after the event. And that's the whole concept for today. So we're going to do some examples and demonstrations of this and put some math to it. So some key things here. What exactly is a system? So what we want to do to define our system is to enclose it so that there are no outside forces. So to define our system, we want to make sure there's no outside forces coming in. Okay, so let me demonstrate what I'm going to be drawing here so that makes a little bit more sense. I'm going to move that down. I put my computer up high on some books so it balances with that. All right, so here I have some carts. All right, so taking a look at this, okay, the purpose of this cart is it has no friction. All right, so a quick look at everybody here. Let's see here. All right, can everybody see this cart? Give me a thumbs up, we good to go with that? All right, DJ, yep, oh, your light is behind you, so I couldn't see your face. You're good, you're good. All right, so I just want to make sure everybody can see this. So this cart, this is a nice track, so it goes very easily and not much friction. So we're going to eliminate a lot of friction. So just to show you an up close picture of what this cart looks like. So wheels on the bottom, so it's not sliding. It has this on the front, which is like a spring, so I can push that in. So when it hits something, it's a spring that bounces off. On this side, I taped some magnets. So I wanted to get some strong magnets on that side so that if another cart comes in, the two can stick together easily and they will stick. On this side, if they collide like that, they will bump into each other and collide and be able to bounce off of one another, okay? So what we're gonna do today is take a look at some scenarios of how these collisions take place, okay? So if this is my cart, what I'm talking about here in the system, that's my system. My hands would be an outside force coming in. My boundaries would be just around the cart. And therefore, if I come in with my outside force and I push on it, I change its momentum, which is what we did over here before break. If I push on it and I want to stop it, I can stop it quickly, right? Force times time, or I can stop it where I come in and I give with it and I slow it to a stop over time. So we were looking before break, how do I come in and change the momentum of this? I can also change the momentum of it by putting more mass on it, right? So now it's heavier. So when I push on it, it has more momentum simply because it has more mass along with its velocity. So now though, if I come in and I have 2 carts, okay, I'm gonna take away those masses. If I have 2 carts, and now the reason we really take a look at conservation of momentum is the event. So something that's really hard to study is collisions, when 2 things come in collide. Also explosions, when things spread apart, or if they collide and stick together. So these collisions are difficult to study in terms of forces because it's hard to evaluate the forces that are there. So in science, we've come up with the concept of a system where I imagine my boundary surface is around out here. So what happens between these things is now an internal force. And if all I have is internal forces, then momentum is conserved. That's what has been found. So it doesn't matter how these collide. What is true is when this one comes in, the event would be the collision or explosion or sticking together. When that takes place, momentum is conserved. So the system, you imagine a boundary, in this case is going to be both of these carts, okay? So both of these carts coming together will be my system. So let's draw this again on our board. I'm going to pull that up closer for you there. And just, you can see that better. So in our conservation of momentum, we're going to get rid of the forces because we're not going to allow any external forces. So mathematically, what this paragraph says over here is if I have a system consisting of however many objects I want, let's say cart 1 and cart 2, my system is those like that. What happens inside that boundary surface is part of my system. So I don't care what forces are going on. What we're saying is if we have an event take place, and this is before, whatever the event is, let's say maybe they collide, right? And they stick together, 1 and 2. And then after, you have that situation. You still have your boundary around the 2 of them, right? Here they come in, we have the event takes place, and that's afterwards. What this says over here is my total momentum. So I would say momentum of number 1, and remember it's a vector quantity, plus momentum of number 2, right? And I could have a third object in there. Momentum of number 3, however many things you have. So I'm going to say dot, dot, dot. However many objects I have before the event must equal my total momentum after. And I'm going to put a little prime up here to say after. So the subscripts are important. Hopefully that looks like there's a little bit of a glare there, but are you guys all seeing that okay? Momentum prime, 1 plus momentum 2 prime plus momentum 3 prime and dot, dot, dot. So mathematically, conservation of momentum says all of our momentum before must equal all of our momentum after. Ryan?
Can you explain the momentum prime that you put?
The momentum prime, yes. So what the momentum, anytime I use this prime, what we imply with that is after. Okay, so what's a prime symbol on top of something means afterwards. So we're going to use it on velocity and we're going to use it on momentum. Okay. So that's a generic equation right there. Okay, any other questions? Give me a quick thumbs up. We ready to, everybody's got those notes okay? John, you still writing them? That's fine, take your time. I was going to just move mine. So this prime, I'm going to rewrite that over here. Okay, on this side, I'm just writing it a little simpler with only two things. Okay, so I have two carts. So we're going to go back to just using our two carts right here. So as we take a look at these, okay, that's what the equation would look like if you only had two things. What I was trying to draw for you there was you could have more than two things. You can have 10 things, however many things are involved in your problem. So today we have two carts. So let's say I collide them together. Momentum is actually mass times velocity, right? So I'm going to say the mass of object one times velocity of object one plus the mass of object two, velocity of object two, must equal the mass of object one, velocity of one after the collision. So again, we're going to use that prime symbol to mean afterwards. Because after they collide, they're both going to be moving somehow. What we're saying here is, however they were moving at the beginning determines how they move at the end, but the total momentum of the system must be equal.
Miss Reisenweaver,
Yes, Hector.
what are those look like? I know like the little prime marks, but why doesn't the M have the prime mark?
Well, my mass would not change.
Only the velocity would change?
It could, but we would assume, let's say two things stick together. I wouldn't make that a new mass. I would simply say these two, if they stick together, have the same velocities. So I would add my masses up to get my final mass at the end. We'll do some examples of that. But the mass does not have a prime because you make the assumption that the mass of the object itself doesn't change. There is something called conservation of mass. Einstein said we can change mass into energy, and that is true. But in a system, we're going to keep the mass conserved.
All right.
Okay, so we're only looking at changes in velocity that cause a change in momentum.
Okay.
Okay,
Thank you. All right.
so let's do a scenario here. Let's say I push object number one. So the other thing, remember, these are vector quantities. So I dropped off my vector symbol on my velocities. These are vector quantities. I'm going to take to the right to be positive, to the left negative. So I could have a head-on collision where one is coming to the left and one is coming to the right and they collide. How do they move afterwards? So this is when you go back and you replay accidents, how police officers can tell you how fast were you going, who was moving which way, all based on the after effect. And let's say this one is sitting there at rest. So it has no velocity. This one is going to move forward with some velocity. If they collide, what's going to happen afterwards? So in my carts, these masses are all the same. So they all have the same mass. So our first scenario is what happens when two masses that are exactly the same collide, one being at rest and the other one comes in and hits it. Let's take a look at that. All right. So what do we think might happen? All right, so everybody kind of come up with an idea in your head. What do you think is going to happen when I bring these two carts together and one cart is at rest and the other is moving? Okay, so I'm going to bring them together. They're going to collide and they're not going to stick, so they're going to be allowed to bounce off of one another. This one is going to be at rest. I'm going to give this one momentum. It's going to come in and hit this one. Hector, what do you think might happen? What's it?
I think that one of them is going to be at rest, and then when the other one comes in, the one that is at rest will start moving in the other direction. But I think it will be moving at a greater I think the one that was at rest will probably be moving at a greater momentum than the one that was already moving.
Okay,
I'm
so
not really sure.
if this one, let's say, has a total momentum of 5, and this one's at rest, how much momentum does it have?
None.
None. So we have 5 and 0 equal, we'd have 5 plus 0 to give us 5. So one thing you said was this one's going to move off with a greater velocity than this one. If it moves with a greater velocity and they have the same mass, that would mean I get more momentum afterwards than what I had before. So the only thing that there's 3 things that could possibly happen. This is going to come in and hit it. And if this had 5 and 0, afterwards I have to have a total of
5.
5, right? Everybody following our numbers? You guys are great with numbers. So afterwards I have to have 5 to the right. So remember, this is a velocity, this is a vector quantity. So if this comes in having 5, this 0, and we say this one's going to move, one choice is it moves with 5. If this one gets 5, what happens to this one?
Doesn't move at all.
It has to have 0. So one
Wait,
scenario is this one comes in, this moves off with 5, this one stops. So that before I had 5, afterwards I have 5. I could have this one comes in and it moves off with 3, which means what happens to this one?
Has 2.
It has 2. That's exactly right. So this one might move with a faster speed, but then this one behind it slower.
Or
But
they could.
together, they are both moving with velocities, and this one may be 2, 3 to give us a total of 5. What we had before must equal what we have after.
Or it could be 2. Or they could hit each other and then the force could be equal, so they could both have like 2.5.
That's correct. So they could go off that they go off together. But this one's slower than what it was at the beginning. This one, of course, faster because it was 0.
Yes.
Another scenario would be that this one hits it and bounces backwards. If this one bounces backwards, then afterwards, it actually has a negative momentum. So if the 2 collide and this one goes backwards with 2, now I have -2. How much do I have to add to -2 to get 5?
7.
7. So that's one case in which, Hector, this one could go off with a faster velocity if this one actually bounces backwards. So another scenario is this one. They come in and collide and this one goes backwards. But that more than likely is not going to happen because then this one has more momentum going that way than this one did initially. So that can happen in a different case where maybe this one was moving forward. And so those are the scenarios that could possibly happen. Ryan, I see you have a question.
Isn't since they have springs, like both have springs, it's not gonna have a large impact on it because when the one's coming in with the 5 momentum, when the other one that's at rest, it would stop for a while, but then it'll absorb the hit to make the impulse, cause the impulse, and then that means that.
Okay, so now remember, I'm not sure if this will help if I'm understanding your question correctly. Remember, these springs are an internal force. So for this cart, yes, this is applying a force to it. For this cart, this one's applying a force. Equal and opposite reaction and action forces. They, in the system, are an internal force. So we are not saying there's any change in momentum in the system. If I take my system like this, then this cart becomes an outside unbalanced force, and we would look at it in terms of impulse and momentum. And I point over here because that's where we started the beginning of class. But if I'm looking at these two as one system, I'm not worried about what happens here, this force. It's irrelevant.
Okay.
It is relevant in that do they stick or do they push off of one another? But it is understood that they'd be equal and opposite in direction. All right? All right, so here's the scenario. At rest, I'm going to bring this one in, and we had those 3 options. So let's see what happens. So very, very, very slow. We'd almost say that one stops. And this one moves off with the same velocity that this one came in. right? So if I hit them, that one goes off with the same velocity. Ryan? Did you have a question, Ryan? Or are you good?
I do have a question.
Okay.
Oh, my bad.
I'll close that out. I see that you had your hand up. There we go. Okay. All right. So if we were to put numbers to this, let's say this has a mass of 1, moving with a velocity of 5. 1 times 5 would give us 5. This has no velocity, so we have 0 momentum here. On the other side, if this ended up being stopped, my v prime of number 1 becomes 0. My v prime of number 2 had to become 5 because they are of the same mass. Okay? So what would happen if I increase the mass of one of these? And I do the same scenario. So now this one has a greater mass. We're going to do the same thing. This is at rest. This is going to come in and hit it. So that's another scenario. So in the case where the masses were all the same, that was a little easier to kind of analyze the numbers. What's going to happen if this one comes in and hits it and it has more mass than the other one? So before the event, this one still has 0 momentum. This one might have a mass, so let's throw in some numbers. This one might have a mass of, let's say, 5 kilograms and a velocity of 2 meters per second. This one is not moving, so it has no momentum. Afterwards, big mass, that's still 5 kilograms, times something, plus this one has less mass, let's say 2 kilograms. I'll go ahead and get rid of this. Actually, let's make it half the mass. I doubled it. 2.5 kilograms. How fast might it be moving afterwards? Okay, so what we do know, no matter these velocities, what must be true, John, what must be true about the right side of this equation?
That it equals that side.
Which is how much? 5
Uh,
times 2?
is 10.
10, good. So what we do know is my total momentum must be 10 kilogram meters per second over here. So to get that, again, I have a couple scenarios. We know this one's going to end up moving, right? So that's not going to be 0. It could be that if the first one stops again, this one must move, right, Chase? How fast would this be going compared to the original one at the beginning if my first one stops?
Would it be going? Would it be going like as half as fast?
Would it be going half? Well, I have half the mass moving, so my velocity must be
Twice?
twice. Very good. If this one was 0. So if this comes in having twice the mass and it stops, this one must go flying off and going very fast. And that would be because its momentum must equal this one, but if I have half the mass, the only way my momentum is equal to this one is if I double my velocity. Make sense? If this one continues to move, right, if they hit it and it continues to move, then I still will have velocity here. This one more than likely will be, it has to be less than what it was at the beginning, because together they must add up to be 10. So it can't be equal to, because that would already give me 10, which means this one has to be 0. All right, let's test out that scenario and see what we get there. All right, so this one's at rest. I'm going to bring the other one in. It collides. Now, you may not be able to tell, but this one goes off pretty fast. The other one continues to move forward, but slower than what it was. Let me try that again. So it's coming in. That one slows down. That one goes off a little faster. So in that scenario, what happened was this one had less. Let's say it only had 1 meter per second. How fast is this one going over here? So there I would have 5 kilogram meters per second. What has to be that velocity right there? Matthew, what do you think? So that this plus whatever that is gives me 10.
5.
Wow. Well, I need this to be 5, so if my mass is 2.5, what do I have to multiply by to get 5?
Oh, 2.5.
Not quite.
Plus, multiply, sorry. 2.
2. Very good. So this would give me 5 kilogram meter per second, making both sides 10 kilogram meters per second to the right. Make sense? This is an interesting one. With my numbers that I gave you, the smaller one goes off with the same speed this one had at the beginning, but because it had less mass, it could take that velocity and still leave velocity for this one because of the momentum. So that's why it's important to take a look at momentum is not just velocity, but mass times velocity. Okay, good. Let me take away the mass. All right, let me give you guys all a quick look here. Everybody good going all right?
Yep.
Good, good, good. All right, Roth, how you doing? Good? All right, so let's take a look at another scenario. So just taking a look at all of this, momentum, conservation of momentum. I'm going to turn these around. Remember, when I turn them around, they are now going to stick together. So Hector, this was one of your questions at the beginning. Here's one. They're going to come in, and now they are going to stick together. So what could happen in that case? All right, so we're going to go back to the beginning. This one's at rest. This is going to come in, and they are going to stick together, I hope. So I tried to make it so that they would stick. All right, Roth, what do you think in this one? I'm going to get rid of our numbers here. Well, maybe we'll keep our numbers. And let's see what scenarios we could have. I'm going to bring this one back down to 2.5. So it's going to be the original mass. All right, so 2.5 kilograms. I'm going to push it in with a velocity of, let's say 2 meters per second. This one is at rest. It has the same mass, but it's at rest, so it has no momentum. Afterwards, they both have a mass of 2.5 kilograms. Times some velocity. That mark is not very good. Can you guys see that? Let's see, this one might be, there we go, much better. Okay, everybody see that better? Okay, Roth, so here's the scenario. One cart coming in with a velocity of 2, so it's going to hit that. 2.5 times 2 is?
5.
5. So we're going to have 5 kilogram meter per second plus 0 equals. Over here, I have 2 masses. They are going to get stuck together. How fast do you think they're going to be moving compared to the original object? What's your thought?
Maybe a little bit slower.
And why?
Because it's 2 masses, not just one moving.
Very good. And for momentum to be conserved, if my mass increases, my velocity has to decrease. Why is my mass going to increase? I'm actually going to have twice as much mass. So how fast would they have to be going? If I double my mass, what has to happen to my speed?
Double your speed?
You just told me I had to go slower.
Oh.
If I double my mass, I should less
decrease.
than. So a scenario, instead of doubling it, I would what might be less than? Instead of doubling, I would multiply by 2, but
divide by 2.
Divide by 2. So what's 1 divided by 2 gives me?
0.5.
Half as much. So we're expecting maybe to go half as fast. All right, ready? So here it comes. They're going to stick together, and it went. I don't have any detectors to actually measure the speed, but it definitely went slower, right? So here it comes in, they stick together, and they move off much slower. Mathematically, how fast would they have to move? What's true is since they are stuck together, their velocities afterwards must be the same. All right, so I'm going to write that down because this is going to be important in your homework. You have a lot of questions about what happens when things stick together. So since they stick, what's true is V1 prime must equal V2 prime, right? Our two velocities must be equal to each other. And then you can just call that a V prime, not put those in as two different variables. To make the math work, each one of these must be worth 1, half as much as they were over here, because I'm going to be doubling this. So then I end up with 2.5 kilogram meters per second plus 2.5 kilogram meters per second. 2.5 and 2.5 give me 5. So momentum is conserved. So if we're in the lab, if I had you guys in the lab, we'd be setting up detectors to tell the speed and actually prove this. But all I can do for you right now is demonstrate that for you. Okay? So, all right. Any questions on any of that? We have a few more minutes left. Hector?
So on that problem, so the 0 represents the speed, 0 represents the momentum or the speed of the other object.
Correct. So the scenario was, this one is at rest, right? So here's my two objects. So the original picture, two objects, one is at rest. So since it's at rest, it has no momentum. But I still want to consider it because I could, we're going to do some other scenarios. What if the two are coming in, right? What if this one is moving already? So this one is moving and this one comes in and hits it, right? So I could have a scenario where this one is moving and then this one comes in and then they collide and move off together. So that's another scenario, right? You're driving now. Notice the best scenario is something like that. Because if you're in a car accident and you see somebody coming in from behind you, they will transfer their momentum, and that's where the damage really gets done. So your best scenario is to move with it. So if I see somebody coming and I have room and you start moving, then you're not going to absorb all their momentum. You're going to allow that to continue to go forward, actually. Okay, so let's see. I only have a couple minutes. Let's do one scenario. Somebody give me something. What would you like to test out? Garrett, give me a scenario. What would you like to try?
I think we tried just about everything.
Oh no, we
really
have
think
lots
about
to
it.
still do. What if mass 2 is bigger? What if I put the mass on here? And it's at rest and I come in and collide with it. What do we think?
Just like take less of the impact. It'll just slowly go off into one direction rather than.
Oh, it could. All right, well, let's put the bumpers on it and not have them stick together, but that they are free to move apart. All right, so let's do that scenario. All right, this has a big mass, little mass. So let's put our math to, because you guys are so good with that. Now, we have a big mass here, but it's still not moving, so there's no momentum, right? So if I come in, oh, is that you, Hector? I'm gonna mute you. There we go. All right, so let's go back to that real quick. I'm gonna leave you with that. What's our thought? Everybody make a prediction. Big mass, little mass coming in, but with a high velocity. What are they gonna do when they collide? Ready? What did this one do a little bit?
That one basically stopped. It actually started moving.
It stopped, but it went back just a little bit. This is the dangerous accident. When I hit something bigger than me, it makes me go backwards. It actually changed the direction of my momentum. mathematically, what happens in that case, this number would have to become negative on this side because it's moving in a different direction. All right, I'm going to end with that thought for you guys to all be thinking about that.
So it's like a card.
So
So it's
Garrett,
like a-
we actually have probably 1,000 more scenarios we could put in here. I could put in
That's like a car
projects.
hitting an SUV.
Ryan, real quick.
Yes. What if they're going in the opposite direction, but one has a greater velocity?
Okay, you want to try that? We're going to do a whole bunch more the next class, but if I move them both and they collide, we did not do a head-on collision yet. So for your entertainment purposes, here we go. That's a good one.
One with the less mass got hit way
Yeah,
harder.
but the one with the bigger mass.
Okay, I'm trying to push them together with the same velocity. Here they come. They're coming in with the same velocity. This one goes out faster. It actually bounced back and went faster. So a head-on collision with something of more mass is actually more dangerous because you end up getting kicked out faster. They kind of swap momentum. This one's momentum turns into this one, and this one has to come back. Conservation of momentum. Before the collision, it was almost zero. After the collision, they kind of fly apart. All right, gentlemen, your worksheet, I am going to assume is going to be a little bit challenging because we just started this. As always, do your best attempt of it. That's what I'm grading you on. I'm not grading you on perfectly correct answers, but rather a well attempt. What's meant by a good attempt? Drawing a picture, writing what you know, what you want to know, right? And then plugging in some numbers if you can. All right, as always, nice to teach you. Have a great afternoon. You need any questions?
Thank you.
Thank you.
I need to take a picture of all this really quick.
You want me to move aside?
Yes, please.
I'll move this, let me move my computer back up. You can do a screenshot. Just for you, Hector.
Thank you.
Good thing I like you so much. There you go. All right.